Question 6. Figure 2 shows a sketch of part of the curve with equation y equals f of x, where f of x is 8 sine half x minus 3x plus 9, where x is greater than 0, and x is measured in radians. So let's make sure our calculator is in radians. The point P shown in figure 2 is a local maximum point on the curve. Using calculus and the sketch in figure 2, find the x-coordinate of P, giving your answer to 3 significant figures. So what do we know about point P? We know it's a local maximum point on the curve. And we know that maximum and minimum points on curves are turning points. We know that turning points have a gradient of 0. So this is where we're going to use our calculus. If we differentiate our f of x, we will have our gradient function, and we can put that equal to 0 to find the value of x at these turning points. So differentiating our function, sine differentiates to cos, and we need to multiply by the derivative of this component, half x. Half x differentiates to a half, so this becomes half times 8 cos half x. Differentiating negative 3x goes to negative 3, plus 9, which is a constant by itself, differentiates to 0. Simplifying this then, f dash x is equal to 4 cos half x minus 3. At the point P, as we've said, our gradient is equal to 0, so we can put our gradient function equal to 0, so 4 cos half x minus 3 is equal to 0. If I rearrange this equation, adding 3 to the right hand side and dividing through by 4, I've got cos of half x is equal to 3/4. On my calculator, if I do cos to the minus 1 of 3/4, so inverse function, I get a value of half x is equal to 0.7 and so on. This is where we need to be careful. At this point, we're going to use the sketch. We've used calculus, and now we want to use the sketch. What do I notice about the gradient of 0 on this curve? Before P, there is a local minima and another local maxima. So P is not the first case where the gradient equals 0. In order to look at this, I'm going to use a substitution. Instead of sketching cos of half x, which is a little bit more confusing, I am going to let u equal half x, and I've got a sketch of cos u. So this is my standard cos curve between 0 and up to 2 pi here. Of course, this would be going on now to 4 pi. On my calculator, when I find the value of u, as I did here, cos to the minus 1 of 3/4, I get my value of 0.7 and so on. This corresponds to the first value on my graph. So when y is equal to 3/4, the first solution is 0.7. Now this will relate to the first turning point on our curve, which is A1. Our second turning point would be 2 pi minus 0.7, which would give me the local minima at A2. But I want the third turning point, which is 2 pi plus 0.7 at P. So U has an endless number of solutions, but I am interested in the third, 2 pi plus 0.7. And so putting that back in, I've got half x is equal to 2 pi plus 0.7, and so on. On my calculator, I can type in 2 pi plus 0.7 and multiply by 2. This gives me a value of x of 14.0 to 3 significant figures. The curve crosses the x-axis at x is equal to alpha, as shown in figure 2, given that to 3 decimal places, f of 4 is 4.274 and f5 is minus 1.212. Explain why alpha must lie in the interval 4, 5. Well, a change in sign on a continuous function indicates that a root exists. Looking at the interval provided in this question, 4 and 5, when I substitute 4 into this function, we are told we get a value of 4.274, which is above the x-axis. And if I put in f of 5, we get the value of negative 1.212, which is below the axis. So within the interval given, 4 and 5, there is a change of sign, and so a root must exist. Part C. Taking x0 is equal to 5 as a first approximation to alpha, apply the Newton-Raphson method once to f of x to obtain a second approximation of alpha. Show your method and give your answer to 3 significant figures. I've taken a formula book extract here. If we can't remember our Newton-Raphson iteration, it is in the formula booklet. So for solving f of x equals 0, x of n plus 1, so the next term, is equal to xn, the previous term, subtract the previous term in the function divided by the previous term in the derivative of the function. So we're given our first term, x0 is 5. Therefore our next is equal to our previous solution, 5, subtract 5 into our function, divided by 5 into our differentiated function. Our f of x is 8 sine half x minus 3x plus 9. If we substitute 5 in, our f of 5 value is minus 1.21 and so on. From our previous question, part A, we know that the derivative function of this is 4 cos half x minus 3. Substituting in our 5 again, we get our f dash 5 is equal to 4 cos 5 over 2 minus 3, which is minus 6.204 and so on. Again, we're going to store this in our calculator. x1 is now equal to our previous term, subtract our previous term in f of x and our previous term in f dash x. Let's look at how to do this on the calculator. So on our calculator, we had 8 sine 5 over 2 minus 5 times 3, so it's 15 plus 9. So our first value was minus 1.21. Now if we hit store and A, that answer is now stored in part A on our calculator. So now if we work out our denominator, so that was 4 cos of, again, 5 over 2 minus 3. And that gave us the value of minus 6.2. Again, if we hit store and B, then those answers are now stored as A and B. In fact, if we just hit shift recall, you can see that you've got A is equal to minus 1.21 and B is equal to minus 6.2. So now back on the home screen on your calculator, we want to find 5 minus our A. To get this again, we could go alpha A divided by our B, alpha B, equals 4.804. And so our answer is 4.80 to 3 significant figures.